Okay, so we're trying to figure out what's the Galois group of a quadratic, all right, quadratic polynomial, and over some field, right? So the deal is, it's by definition the Galois group of the polynomial is the Galois group of the splitting field of the polynomial over f. Now, if the quadratic is irreducible, right, then that means that, so this is going to happen, and what else? A squared minus 4b is not equal to like c squared for some c and f, right? It's not the square of an f element. See, here's a counterexample to this. If I have x squared minus 3x plus 2, well, that's a real polynomial. Its discriminant's not 0, right? The discriminant here is
do you need to have the 0 thing? Because
9 minus 8, which is, sorry,
no,
which is 1, right?
yeah,
Of course, that is equal to 1 squared, right?
yeah.
Which goes to show you that, in fact, we're not in the case that the discriminant's a square of the base field.
Mm-hmm.
So if the discriminant's the square of the base field, what that means is that the base field is the splitting field in this case. Because that is tantamount, if the discriminant's a square, that means when you can complete the square, you can complete the arithmetic of completing the square completely just using numbers from the base field, which means that the polynomial is split. So the base field is the splitting field. And what are the automorphisms from, what's the automorphisms that fix R over R? R fixing automorphisms of R, it's just there's one of them.
Yeah, the identity.
It's just the identity, right? So the trivial, if the, you know, what's the word here? If the discriminant is the square of something in the base field, then the Galois group is trivial. If the discriminant is non-zero, then the Galois group is up to isomorphism, the cyclic group of order 2. And so, like most commonly, we think about x squared plus 1, and then we know that the automorphism of the Galois group is just straight up, you know, conjugation, complex conjugation, right? Another example, of course, if we have x squared like minus 2 over the base field 2, right? Then in this case, what's the discriminant?
Root 2? Or, yeah,
Minus,
something like that.
I guess 8, yeah. Because minus a minus 2, here b is equal to 8 minus 2.
Yeah.
And so, of course, that's not equal to 0. And also, 8 is not equal to a rational square, right?
Wait.
You pick any p and q, you cannot take a rational number, square it, and get 8. Right? Because 8 is 2 root 2.
Yeah.
And the root 2 is poison from a rational perspective. So anyway, the discriminant is not a rational square, therefore, in this case, we're in the irreducible case, and indeed the splitting field here is q adjoin the square root of minus 2, the square root of 2, right? So q adjoin square root of 2 over q. If we look at the automorphisms of that, right, which is the Galois group, is this, right? Of that polynomial is that, and as you know, it's just the identity map and the what? The sigma map, which is defined by what? Sigma of square root of 2 minus square root of 2. Right? So again, up to isomorphism, that's C2. So I just broke my brain a minute ago when I tried to think about the Galois group of a polynomial which factors over the reals. The reason is it's a silly case. I mean, there's kind of nothing to see here. Now, the cubic case, what are the possible Galois groups of a cubic polynomial, right? That's the next thing that we're talking about in section 4.6, 14.6 rather. And so just to run down the possibilities here. For degree 3. So here we're looking, come on, where'd you go? So here he's like f of x cubed plus ax squared plus bx plus c. And for this, the discriminant turns out to be, I'll just write it down. I'm not going to derive this because I want to spend our energy on other things today. A squared b squared minus 4b cubed minus 4a cubed c minus 27c squared plus 18 abc. That's the discriminant for the cubic.
Good
All
old
right.
Cardano.
No, I don't know about that. Not sure this has anything directly to do with Cardano, this one. I mean, everything does with cubic, of course, but I'm not sure if that particular formula is his or anything like that, right? So different choices. So if the cubic polynomial is reducible, then what does it do? Let's think about different cases. If it's a reducible cubic, that means it can either do what? Linear times irreducible quadratic, right? Or it can do what? It can do linear, 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 right?
Yep.
And he says,
If it's linear, it's reducible, sorry. Yeah.
right, so this one, and let me just call this, let me say that G is equal to the Galois group of f of x, okay? Okay, and we're thinking about this over the rationals. So in this case, you get the Galois group is, again, essentially f isomorphism Z2. In this case, you get the Galois group is just trivial. For much of the reasons that we went through in my preliminary example for the real one that factors, right? The splitting field, if it factors into a triple of linear factors, that means that Q is its own splitting field. What are the automorphisms from Q to Q? There's just one, right? So that's reducible. Now, if it's irreducible, so he calls that case A. Case B, irreducible. Then what? He says, then a root of f of x generates a degree 3 extension over f. Right, so the splitting field over, the degree of the splitting field over f is divisible by 3. So then the if k is equal to, let's say, no, I'm saying q, but he's got f in no input, but anyway, I'll just say q. I join the three roots, right, alpha 1, alpha 2, alpha 3. So the point is that, the degree of k over q is what? It's 3. Well, I can't say that. It's divisible by 3. I think I could say it's equal to 3. Why can't I say it's equal to 3? Oh, it's divisible by 3 because any one of these things is a degree 3 element. So it has to be divisible by 3 because like q adjoining alpha 1 is a subfield of K, right? And so that is degree 3.
Ooh, so, but K over Q is less than or equal to 9?
Well, we had another theorem, I think, that the degree of the splitting field over a polynomial of degree n is less than or equal to n factorial.
So 6.
6, yeah. So, in other words, but the larger point here, of course, is that we can view G as a subgroup of S3, right?
Yes.
And so we need a subgroup of S3, which is what? Let's see here. Well, since the Galois group is a subgroup of S3, there are only two possibilities, namely A3 or S3. So, or S3. Now A3 is the alternating group. So if you have any, you can think about it in terms of cycles. It's the group of permutations of, I believe, even length. So this is explicitly the identity, and then if I remember right, it's like 1, 3, 1, 1, 3, 2, 3, 2, 1, 3. Oh, curses. What is A3? Come on. Sadness, I should remember this. What are the cycles of length 2? Excuse me, what are the permutations of order 2? Excuse me.
1.
So,
one,
what,
two.
What does S3 have in it?
1, 2.
You got 1, right? You've got the 1, 2, 3 cycle. You've got the 3, 2, 1 cycle.
Yeah,
And you've also got
2, 3,
1, 2, 1, 3, and 2, 3. So these
Are your 6?
1, 2, 3, 4, 5. Oh, that's it.
Yeah.
Okay, so the thing I'm forgetting, because I'm a little rusty at the moment, is these can be written as the product of transpositions. Like 1, 2, 3 we can re-express as like 1, 3, 1, 2 maybe. Let's track through this. 2 goes to 1, and then 1 goes to 3. So 2 goes to 3. Let's plug in, try plugging in 2. 2 goes to 1, okay, I just did that. Try plugging in 1. If I plug in 1, 1 goes to 2, and then it goes nowhere. So 1 goes to 2. Let's try plugging in 3. 3 goes nowhere here. 3 goes back to 1, so 3 goes to 1. So this is equal to that. This product of transpositions is this 3 cycle. And this one, it must be the other way around. It must be 1, 3, 2, 3 or something, or 1, 2, 2, 3 maybe, I don't know. I'm just guessing. Let's try it out. 1, plug in 1. 1 is supposed to go to 3 here, right? So plug in 1. 1 goes nowhere with 2, 3. 1 goes to 2 here. Oh, this wasn't it. So let's try 1, 3, 2, 3. See if that's the one. Maybe. I don't know. We'll find out. All right, so where's 1? 1 is supposed to go to 3. 1 goes nowhere. 1 goes to 3. That's a good sign. 2. Where's 2 go? 2 goes to 3 here. 3 goes to 1. 2 goes to 1. Ah, good. Where's, which one did I not check yet? I forgot. Anyway, I'm pretty sure this is right. The point is, A3 is just got, it's got the identity permutation, and it's got 1, 3, 1, 2, and 1, 3, 2, 3. Right. And by the way, of course, in the 3 cycle, as 3 cycles, those are 1, 2, 3, and 3, 2, 1, which by the way are inverses. Right? If you compose those, you get the identity, because they do the opposite thing. 1 goes to 2, 2 goes to 1. 2 goes to 3, 3 goes to 2, vice versa. So those are inverses. So that's what A3 is. And so what A3 really is up to isomorphism. A3 is the cyclic group of order 3. Right? This is isomorphic to 3. see, because like, this is kind of like, this is like 0, this is like 1. What's the order of 1 in Z3? It's
0, 1.
Well, it's 3. Right?
In Z3, 0, 1, 2.
Or 3. And these have order 3. If you compose them with themselves, you have to do it 3 times to get back to the identity. If you compose this with itself twice, I believe you get to here. I want to say 1, 2, 3 times 1, 2, 3 is 3, 2, 1, must be. Anyway, this is Z3. So if we have a irreducible cubic, the Galois group can either work out to Z3 or it can work out to the full S3. And we've seen the S3. Like when we looked at x cubed minus 2, remember that one, the the splitting field had to be, we had to have
root 3.
Cube root of 2 and I, and
Yeah.
it turned out that was degree 6 extension.
Wasn't it root 3 too or something?
Yeah, the third root of 2 and I. And that was the degree 6 extension, which corresponds to the Galois group, of course, being, because remember the number of automorphisms is equal to the degree of the splitting field over the base field as well.
Yeah.
So that's kind of the possibilities in the cubic case.
You said the number of automorphisms is equal to the degree
of the splitting field.
This is 9.
What is degree now? What's 9?
The number of automorphisms.
What do you mean?
Well, it's not 3. It's
I mean, there's 2 different, I'm talking about 2 different cases.
okay.
There's one kind of polynomial, there's one kind of irreducible cubic which could have a Galois group which is like A3. There's another kind which could have a Galois group which is like the full S3. The next paragraph kind of explains what the discriminant has to do with that. So he says that the Galois group is A3 if and only if the discriminant is a square. So this case right here, this case, this is when D is equal to like, Q squared for some Q in the rationals in my current context. And I'm assuming the other case, right? Come on. Okay. He says, let's see here. If D is not a square of an element of F, then the splitting field of F of X is degree 6 over F. Hence the field is F adjoint theta and a square root of D for any one of the roots of F of X. Like, actually the splitting field, K, is Q adjoin, alpha, let's say, and alpha I, right, and the square root of D. This is for D, not square, Not a rational square. It's just that, and which is what we saw, right? Like, for example, the x cubed minus 2 case, that example we looked at, right? There we had the splitting field was Q adjoin the third root of 2, right? And an I. So what is the discriminant for this example? That's something we never calculated. What is the discriminant for this guy? So you gotta compare this mess, right? What's A, B, C?
We have 0 and the 0, 0, 2 minus 2.
Yeah, A equals B equals 0.
0, 0,
C,
0.
C equals minus 2, right?
0. So you get minus 2 times 20, or 4 times 27, which is like 108.
Is that what we get?
Yeah, because everything zeroes out.
Except for?
The 27 times 4. It's like 108.
Is it 108 or is it minus 108?
Minus 2. Oh, wait, it's a square. Minus 108.
Minus 108, okay. So, what is the square root of minus 108?
Oh, between 10 and 11.
Between 10 and 11 is not a helpful comment. But it's funny.
You can split it up, right? You got 2 and 54.
I believe this is 7 times, isn't it 7 times
2, 54, 26.
Oh, is it 27 times 4?
No. It's 254, 4 times 26, 6 times 13.
I think it's 27 times 4. Like,
yeah.
25 times 4 is 100.
We already did that.
What?
To get 108, we had to multiply 27 times 4.
Oh, yeah, sorry, I forgot. But that's useful though, because that's 2
20
times 3 times this, not 3 times.
It's just 2 square root 27 minus 27.
Yeah, 2 times the square root of minus 27, which is 2 times
I.
yeah 2i square root of 3, I think. Well, I mean 3 square root of 3, right?
Yes. I was like,
Hey, that's no bueno. I want I. I want something I can clearly get I from. Like, I don't know how to take the 6, I mean this is 6i cubed root of 3, right?
did we miss a C somewhere?
6i
Oh,
cubed root of 3. I mean, that's lovely. But I don't see how to get rid of the square root of 3 and just get back to I. If all I got to work with is the cube root of 2.
these are all zeros.
Well, I don't know. Because I don't see what we did wrong. I mean, it's definitely minus 108 for my C being minus 2. So,
C's minus 2.
I don't know how to reconcile this with their claim on page 613. My only hope is that the formula for the discriminant's wrong. Because I really can't, I know that this, oh wait a minute. I'm an idiot. So I'm forgetting our results. I'm forgetting it. Never blame yourself. That is moral story here. So what are the zeros of f of x?
Root 3
So we've got x cubed
minus 2.
equals to 2, which means that x is an element of the third roots of 2, which include what? Include, yes, the third root of 2, but also e to the 2 pi I over 3 cube root of 2, right? And e to the 4 pi I over 3 cube root of 2, right?
Yeah.
That, in turn,
Oh yeah.
that remember,
Root 3s.
that gave us the, like, those were the minus 1 plus I root 3 over 2,
Yeah.
and then the other one was like, you know,
Was it,
Minus 1 minus I root 3 over 2. These are
yeah.
the third roots, primitive third root of unity and the square of it, yeah?
Yeah.
The point was, when you divide two of these guys, you can divide them and then you cancel out the cube root of 2, and then if you just tilt your head and squint, it's not I that's adjoined. That's bogus. Totally bogus. It was I root 3 that we had to adjoin. It wasn't just I alone, it was I root 3.
Yeah.
And now that makes sense, see, because the discriminant told us. That's actually really cool, because if you see that, I mean, so, you know, for an arbitrary problem, you could calculate the discriminant and, you know, if it's not equal to 0, right, and if it's not a square of the base field, then you know that you're going to adjoin, like it says here, D is not the square of an element, the splitting field's degree 6. So, I mean, if the discriminant's 0, then your, you know, degree, your A3, your Z3 over the splitting field. And the, so let's see, what was it? In the split, it just splits over, the splitting field is just F adjoint theta, I think, or F adjoint alpha in our notation. So you just adjoin any single root of f of x. So this case, the splitting field would be like just Q adjoin
Root 3
root 3
over 2.
or root 2. Although that doesn't work for this one, you know. So like if you wanted to make that happen, I don't know how to make it happen right off the top of my head. Those things, I don't have a good example of a polynomial which has this as its splitting field. Although I think we knew that, maybe you could go back to the cyclotomic section and make it happen. Let me not continue on this path. So I just want to point out there's some really neat things that can be gleaned about examples if we look at this discriminant idea and study what it does. Now the story for polynomials of degree 4 is much, much more complicated, because you can either have polynomial of degree 4 split into linear, 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 or a product of two irreducible quadratics, or one irreducible quadratic and one pair of linears that split.
Yeah.
And, well, you can look at it. There are a bunch of different ways that the roots for a quartic can be permuted. So the possible permutations that are, you know, that can be found there are many. And it takes them about 2 pages to enumerate the possibilities. So, that said, this is Galois theory by Joseph Rotman. The first time I taught Galois theory, I used this book because my brother recommended it. And it was good, but I just, you know, thumb and foot is both frustrating and freeing. It's freeing just because it's like, it's got a much more complete discussion, right? But at the same time, it has a lot of stuff that you're not going to be able to cover. So there's always this kind of like battle.
So is Galois theory like its own class sometimes?
Oh yes, you can definitely take a class on just Galois theory in many graduate programs. And so what I'm doing at the moment is, of course, not a full course of Galois theory, right? This is just a first look at it. And certainly I'm not an expert in Galois theory, but I think it's important for students to be exposed to these ideas, because it's one of those, you know, famous things. And first of all, it's like, why are we studying group theory at all? Well, a lot of it's because of Galois. I mean, he used group theory to solve this standing problem of high school algebra. Well, for us now, high school algebra, right? But so that's pretty neat. And this idea of looking at the automorphisms and studying the relation between fields and groups, that kind of interplay.
I just think it's cool that he transformed problems.
Yes.
Like,
totally agree. That
he said, no, I don't like this problem. Here's this problem showed in this way.
Right. All right, so
I think that's where all the cool math is. This is not why topology is a big tough subject. they're solving things in topology.
Yeah, topology is weird. So this is the section from Rotman's book on classical formulas. All right, so here we go. So first of all, definition. If you have f of x equal, say, r to the n, x to the n, plus da-da-da-da, you know, r2x squared, then, oh, I messed it up already. Oh, come on. You know the thing's messed up, Audric, is I got more sleep last night than usual. So this is my reward. All right.
Rn minus 2.
So it's missing
On purpose?
the next two leading order term. Yes, on purpose. This is called a depressed polynomial.
Is it medicated?
Is it mitigated? I had a student once who came and told me, he's like, he had a result he was very sad about, but he was happy. And I was like, what are you talking about? And after a long time, it was explained to me, he found a way to do something with depressed polynomials on the problem we were working on. It's just like, Nathan, that would have been very, very funny if I knew what a depressed polynomial was before you explained it to me. But at the time, I did not. Okay, so it was before I taught Galois theory. Lemma, here's his lemma, 43. If f of big X equals an big X to the n plus da-da-da-da, you know, usual song and dance, then f tilde of x equal to big f of x minus an minus 1 over n is depressed. So you can kind of see the way that works by just looking at what's x minus an minus 1 over n to the n power, right?
Yeah.
So you have an, you know, x to the n plus n times an minus 1 over n, x to the n minus 1, right? The minus, rather. Yeah. Plus stuff I don't care about. So that's what happens there, right? So when you take this, and then
that's nice.
and then you subtract,
You get alternating plus or minus
right?
with the same thing.
Yeah, so like the next term down, you're going to end up,
Plus an minus 2 to the xn minus 2.
yeah, then an minus 1. Right, so that picks up things like, for example, an minus 1, x to the n minus 1, and then stuff, right?
Yeah.
But the point is, the only way you can ever get to the n minus 1 power in x is from either what? From either the first term or the second term in the sum of f of x minus a sub n minus 1 over n. And so, as you can see what happens, the next to the leading power terms cancel. And so the details are ugly in general, but this is clear. And Rotman, as is his style, gives a much more elegant proof in the book, which I will not give. Okay. So what I'm going to instead do is talk about quadratic. So what does this look like for a quadratic? What does this trick look like for the quadratic case? So quadratic, you have big X squared plus bx plus c, right? Here's my f of x. So f tilde of little x is f of what? X minus, supposed to do b over 2, right? Which is x minus b over 2 squared plus bx plus c, which is what? I'm an idiot. That was supposed to be little x. So what's that work out to? F tilde of x is what? So we get x squared plus c. Now the dx terms cancel, right? But what happens, there's also a plus b squared over 4 and a minus b squared over 2, which gives us a net of minus b squared over 4. He says one obtains the familiar roots for the original quadratic. Oh, I've missed part of my lemma. I'm an idiot. Well, we've already covered that today. So here's the missing part of the lemma. Moreover, if u is root of f tilde of x, then u minus a sub n minus 1 over n is root of f of big X. So that's actually the part he has. I think he doesn't prove. I actually don't think he proves this in the book. He proves that. That's easy to prove. Right?
Yeah.
Because like if you have f tilde of u is equal to 0, well, it's also equal to f of u minus a sub n minus 1 over n by definition. So, yeah. Hooray. Now, but what does that say then? So we can solve this equal to 0 easily, right? This says x squared is equal to b squared over 4 minus c. So x is equal to plus or minus the square root of b squared over 4 minus c, right? In other words, if I use the notation of my lemma, u has, f tilde of u equal to 0, right? So then what's the lemma say? What's the solution of f of x equal to 0? F of x equal to 0 as, what are we supposed to do? U minus b over 2, which of course is minus b over 2, plus or minus the square root of b squared minus b squared over 4 minus c. And as you know, that's up to a scrambling of letters, just a quadratic formula. I've never taught solving the quadratic in this fashion. Right? We are well off the beaten track in terms of high school algebra. No one solves the quadratic like this. Right? We just complete the square and do it. Like, we don't make a substitution to remove the linear term. Okay. So then what?
But isn't this a depressed quadratic? No, it's a real
No, it's
quadratic.
just it's the real deal. Okay. Next up, he says, before discussing formulas for the roots of a polynomial f of x of higher degree, we should say that if f of x is a polynomial with coefficients in the integers, we should first use exercise 63 to see if it has any rational roots, which, whatever this exercise 63 is. You'd have to ask my abstract algebra class of like 2017. So if u is the root of a cubic polynomial f of x, for example, then so one of the things you do is once you have one root of a cubic, you can take the cubic and divide by x minus the root. That will give you a quadratic, which then you can solve. Right? So if we can find one root, we can find the others by doing a long division and solving the corresponding quadratic. That's one way to approach it. But I think that's just kind of a, hey, point of order. This is a simpler way to solve these before we get into the more fun formulas. So let's talk about the more fun formulas. We'll have to remember this lemma.
Okay.
And let me, again, as I told you before I put the video, the camera on today, what I'm showing you right now is so much simpler than what's in Numb and Foot. Like, so much simpler. Because as usual, Numb and Foot is not content to just, solve the problem. It has to talk about the problem in more abstractness. A squared, x cubed plus ax squared plus bx plus c. So here's your general cubic. Right? And the depressed cubic, we can depress it and we get g of x equal to x cubed plus qx plus r, right? Now, so what is that? I mean, if this thing is, let's call this thing f of x for a second, big X, right? Then, I mean, if we were sticking with the notation of the lemma, we would call this f tilde of x, right? And it would be what? It would be f of x minus y. A over 3. But just for the sake of nicer names, he's going to call this thing g of x. Okay. So you can figure out the formulas for q and for r in terms of the original ABC. It's a straightforward exercise, right? So like we'd have x minus a over 3 cubed plus a times, x minus a over 3 squared plus b times x minus a over 3 plus c. Right? That would be g of x, right?
Yeah.
And well, we don't have unlimited time today, so I better not actually put it out. Yeah, I better not.
Yes, this is an algebra thing. I can hammer this out.
Yes.
I'd probably get very mad once I miss a minus sign, but it's fine.
I'm sorry, I wanted to do that. Okay, anyway. So this is our depressed cubic. And he says the coming formula is essentially due to Scipio del Ferro, and a similar formula that was discovered by Tartaglia about the same time. Both appeared in print for the first time in the book of Cardano, and 1545 is Ars Magna. And of course that video you sent me has much more speculation on the history there. So he says let g of u be 0. In other words, let u be a root of g of x, okay? And choose y and z such that u is equal to y plus z. Right? Then u cubed will be equal to y plus c cubed, which will be y cubed plus 3y squared z plus 3yz squared plus c cubed. And so if you tilt your head and squint, you can see what you got there is y cubed plus z cubed plus these two terms in the middle, right?
Mm-hmm.
We can rewrite those as, he says we can rewrite those as 3uyz. See if that makes sense. So when you put in u as y plus z, you get a y squared z, but you also get a z squared y, which is what we have up here with the 3. So that's just, yeah, kind of sneaky. And he says, therefore, y cubed plus z cubed plus 3yz plus q times u plus r equals to 0. So what he's doing here is he's using g of u equals to 0, we get, see, because g of u would be u cubed plus qu plus r equal to 0. So when you plug in u into x cubed, you get this two terms, but you also get that term, but he's just taking this and plugging and getting it over there. So like this, as well as these, are all coming from, you know, that u cubed. All right. So far, we've imposed only one constraint on y and z, namely that u is equal to y plus z. By exercise 68, all right, we may impose a second constraint, namely that yz is equal to minus q over 3. So this y and z were these numbers such that they add to give the root. And now he's supposing that you can also insist that the product of them be q over 3. All right, minus q over 3. And homework exercise justifies that, okay. He says, so that in equation 1, this is equation 1. So what does that mean? If this is true, so suspend your disbelief for a moment that this can be done, all right? Admittedly, that's a homework exercise, right?
You just get yz plus r, or sorry, y cubed plus z cubed plus r.
Y cubed plus z cubed
Plus r
equals to minus r, right?
Yeah.
That's from follows from the equation right above it, right? And what else do we get? We get y cubed, z cubed equals to what? So just cube this equation, right?
Oh, yeah.
It gives us
Q over 9.
yeah, minus q cubed over 27, right? Got to cube it, right?
Oh, yes.
So we have two equations and two unknowns. The two unknowns being z cubed and y cubed. Remember, q is given here
Yeah.
from the original problem statement. So can you solve those two equations that I just wrote in blue?
Whoa. Do we have R, Q? Oh,
R and q are given
okay.
by the algebra we didn't do. They're somehow complicated, they're somehow related to the given a, b, and c
Okay.
in some kind of way, which we could figure out if I had another 10 minutes. But, so, well, let's see here. If we want to just keep the y cubed, right? We'll get y cubed. Z cubed is what? Minus what? Q cubed over 27 y cubed equals to minus r. So I just substituted this one. I solved this for z cubed and I plugged it in.
Yeah.
And then multiply this by y cubed. We get y cubed cubed squared rather, plus r, ry cubed minus minus
Over
q
27.
cubed over 27
We get a quadratic.
equals 0, which is indeed quadratic and cubed. All right, then what? So that gives us y cubed equals 1/2 of minus r plus square root of r squared plus 4q cubed divided by 27. All right. And going back to this equation here, I'll call it star. So star
Oh, we just sub in for YZ.
yields what? Yeah. Z equals to minus q over 3y. Is that obvious? So, well, okay.
Not directly, but yes.
So the point is, it's the y that's given by this above, right?
Mm-hmm. Wait, but don't you get 4y cubed? Oops.
So you put this all together. Fine. To solve for y, what would you do?
Yeah, you just cube the whole thing, but
Yeah, the cube root of it. So this clearly shows you how to find y in terms of
Q and R.
q and r, which are given after the depression, step by dilemma. And this, once you find y, then you can find z like that, right? Once you have the y and the z, you put them together. So u equals y plus z. So we've now obtained a formula
Yeah.
for the root in terms of the coefficients of the depressed polynomial. And he says, having found one root of g of x, we can find the other two roots as the quadratic of g of x divided by x minus u. He says, or there's an explicit formula, here's an explicit formula for the other two roots, just using, well, we know what to do. So, well, you know, we can either put y equal to, let me call this, I need to, just to give myself I need to give a name to this whole expression here just to make my life a little bit easier. I'll call it Pac-Man. Okay, so, so we can either put y equal to the cube root of Pac-Man, right? Or, what else could you do? You could do e to the 2 pi I, right? Over 3 times the cube root of Pac-Man, right? Or you could do e to the 4 pi I over 3 times the cube root of Pac-Man. These are all solutions of y cubed equal to that, right? And what are the corresponding z's? So z is, you know, minus q divided by 3 cube root of Pac-Man, right? Or minus q divided by 3, you know, e to the 2 pi I over 3. I should have found a more compressed notation. Or, now he has a more compressed notation. I'll show you how Rotman writes it in his book here in just a second. So he puts them like this. His notation is this. He says it's minus q over 3 omega y, or it's z over omega, or it's omega squared z. What is this z? Well, I mean, let's, well, I don't think I'm wrong in what I've written. It's just he's got a. All right, so, but, okay, so these, you have to add this and that. No, fine. Let me just rewrite this a little bit. Curses. So you've got y. You've got y. Let's say omega y. Omega squared y. This is our u, and then our good grief, this is our y, quote unquote y. So this is where it gets a little dicey, and I see why he's not written this equation in your z. So the corresponding z here is what? It's minus q over 3. No, good grief. Let me not write, this here is not helpful. So minus q over 3y, or this one would be, you know, minus q over 3 omega y, or minus q over 3 omega squared y. So he just, all right, so